Okay, so let's do this example problem. 6-hour storm rains on a 25 square mile drainage watershed. Records from a stream gauging station draining the watershed are shown. Part A, construct the unit hydrograph for the 6-hour storm. Okay, so the shown here is the table on the left with the data and then the figure on the right showing the same data. So we go back up to our steps, which are shown at the top. Part 1, start with the storm hydrograph, which we already have. Part 2, if necessary, separate into parts to find the runoff portion. We can see from this hydrograph that the flow rate at the beginning and at the end is 0, and thus there is no base flow. So we don't have to separate this into its parts. So we're already, step 3, find the total runoff volume as the area under the curve. So I'm basically calculating the area of all of these rectangles in the hydrograph on the right. And so in order to do that, I'm going to have V equals, we've got 3 hours. At 3 hours, if we're looking at the first step, 3 hours times 400 CFS. And then we're going to be adding 3 hours times 1300 CFS and so forth. So 3 hours times 400 plus 1300 for that second interval, plus 2500 for the next interval, and so on, until we get the entire amount, which is 3 hours times 9500 CFS. And this is cubic feet per second, this is in hours, and so we have to multiply by 3600 seconds per hour. And we wind up with a volume of 1.026 times 10 to the 8th cubic feet. Okay, so that's our volume. That was step 3. Now we need to divide the total runoff by the area of the watershed to calculate the average depth of excess precipitation. So V equals A times P average. So we have 1.026 times 10 to the 8th feet cubed equal to our area, which was 25 square miles. We are going to want to get this into square feet. So we're going to multiply by 5,280 feet per 1 mile, and then square that. Multiply by P average. So we're solving for this P average here. And when I do this, P average equals V over A. And I get 1.766 inches. Okay, so if 1.766 inches of excess precipitation, runoff precipitation, fell on a watershed, i.e. that portion that was more than infiltration, over this 25 square mile watershed, I would get 1.026 times 10 to the 8th feet cubed of runoff. Okay, so now my last step is to divide every point on the runoff hydrograph by this number, 1.766, to get my unit hydrograph. Okay, so what I'm saying here is that this hydrograph that I'm looking at, this actual data I recorded, corresponds to a storm whose excess precipitation was 1.766 inches. I want a hydrograph that corresponds to a storm whose excess precipitation is 1 inch. So if I divide each ordinate on here by 1.766 inches, I will get results that correspond to a 1 inch storm instead of a 1.766 inch storm. We're assuming, again, this is a linear relationship. Okay, as the precipitation scales up, the runoff scales up as well. Okay, so I'm going to now go up to this table here, and I would say, what is my unit Q in CFS. And I'm going to divide each of these. This 400, I would do divide by 1.77. This is going to be 1300 divided by 1.77. And I'll get some results here, which are going to be my new Q's. So for this first one, it would be 226.5. For the second one, it would be 736.1, and so on. Okay, so you see how that works. So for if it was 1.766 inches of excess precipitation, I'd have 400 CFS. For 1 inch, then I would have 226.5. So after I do all of that, I'm going to have my results for my unit hydrograph, and I'd be done. All right, so then part B says find the runoff rate at t equals 15 hours from a 2-storm system if the first storm drops 2 inches of excess precipitation and the second storm drops 5 inches of excess precipitation starting at t equals 12 hours. Okay, so again, we're looking over here at the right at a hydrograph that was for 1.766 inches of excess precipitation. If I drew the hydrograph that starts at time equals 0 and is a 2-inch excess, it's going to start at the same time, but it's going to go quite a bit higher. It's going to 2 inches instead of 1.76. And then we have another hydrograph that starts at t equals 12, which is right here, and goes up, but it's 5 inches, so it goes way up here and then comes down. And we're asked what's the runoff rate at t equals 15 hours if we have these two storms together. Okay, so we're gonna have to add the results from these two at 15 hours. What is this one plus this one? That's what we're trying to get. Okay, so from the first storm, we're looking at the first storm starts at time equals 0, and we're looking at what is the runoff rate at 15 hours. 15 hours after the storm starts. So we look down at this table, and we see that at time equals 15, we have 1,200 CFS for the storm we measured. So Q is equal to 1,200, but then we want to divide that by our 1.76, or 1.766. That will give us our unit hydrograph value. Now we're going to multiply that by the intensity of the storm, which was 2 inches of excess precipitation. And that will give us the runoff, the Q, from that first storm 15 hours after it started. But then we have to add what's going on from the second storm. The second storm starts at t equals 12 hours, and we're looking again at 15. So 3 hours after that second storm starts. And we're looking here, and we see that it should be 400. So 400, but we're dividing by 1.766 again. This, again, is the unit hydrograph value. But now we're multiplying that second storm by 5 inches to get its actual value. And that's going to give us our total value, which is 2,492 CFS. Okay, so you can see how we took a measured storm event that wasn't for a 1-inch excess precipitation, it was for 1.766, and we were able to use it as a tool to get results for multiple storms of different intensities. What is the runoff from those storms? Okay.